Hello. Okay, hello. I know at least one word in Italian, silenzio. Is it right? Yeah, okay. I'm happy to start. My name is Grimm. You see it here. I'm a software developer since 1999. Since 2016, I'm an independent trainer for C++ and a little bit of Python. And as I often said it, since 2016, I only do that stuff I love. I just teach C++. Okay, today I want to talk about, for me, the most important feature which we will get with high probability in C++20, that is concepts. With C++20, we will get 5 big features, really 5 big features which will change the way we program. Concepts, of course, but also modules, coroutines, ranges, and contracts. I mention that explicitly because today there are 2 talks also to modules and to coroutines. From my perspective, you should visit them. Okay, let's start. These are the sponsors. Okay, we are grateful to them. Now let's start with the important stuff, the more important stuff. First, I want to give a short overview. What are concepts? Which problems they will solve? Then I talk a little bit about the long history of concepts. Then maybe it's a little bit more boring, but I talk a little bit about this, the syntax of concepts, how to use them. Okay, then I come to the fun part, which is the placeholder syntax, which from my perspective is the key part of concepts, because the syntax in C++ becomes a lot easier to use. In particular, a lot easier to define templates. As I often mention it, the future of C++ speaks templates, but a lot of people don't know it. Then I come to syntactic sugar. This means it's nothing new, but it's in a new way to define concepts. And at the end, I talk a little bit about defining your concepts. Honestly, well, wait a second, I will say it later. Yeah, later is now. Pantarei, what does it mean? It's from Heraclit, it's from Greek. Oh yeah, you are a little bit connected to Greek. It's from Greek, and it says, it's flowing. It means the river will look tomorrow different than today. That means, from my perspective, maybe a few features will change a little bit, but not the feature concept. So it's still in flux. It's still moving. Okay. A first overview. From my perspective, we have 2 wrong ways in C++. We can define a specific function which accepts a specific argument of a specific type, such as int, double int. Or we can do it totally generic by using a generic function, a template, a function template. Both ways are totally wrong from my perspective. What is wrong with the first way? You don't want to define a function for an int, for a double, for a long, for a short, for a bool, for... You don't want to do it. Therefore, we have convenience features such as narrowing conversion, integral promotion, which are also kind of the problems we have in C++. What is the problem with a generic function? You define a totally generic algorithm, which will only work for half of the types. For the another half of the types, you will get a terrible error message. And you know, C++ is well known for that. And now we have something in between. And this in between is concepts. First, a short example. You see here, I defined a function which only takes an int. And I can invoke it with a double. At the end, I end with an int, but I started with a double. That is narrowing conversion. It depends on your compiler, on your optimization flag and stuff like that, if you will get a warning or not, but it's an issue. That is one issue we have. The another issue is this one. This is GCD, based on the Euclid algorithm for determining the greatest common divisor of 2 numbers. That is generic. that is parameterized on T. It will work for int, but it will not work for float, or sorry, in this case it's a double. Why not? Because double has no idea of the modulo operator. That means the template will be instantiated, and during the process of instantiation you get the backtrace of all what happened before, and this could be pages of errors. That is the second problem we have. Too specific, too generic. And now we have something in between, and that is templates. Here only a few ideas. I will come to the details later. First of all, you can express requirements to the template as part of the interface. This type must support the concept of integral, for example. Concepts also support the techniques we like, such as overloading of function or specialization of function templates, of class templates. They improve drastically the error measures if you do something stupid, such here before invoking GCD with a double. You will get a nicely readable error message, which is not a side product of the wrong instantiation, but it's a product of the template declaration. This will not fit. You cannot invoke a double, cannot use a double to instantiate something which needs an int. And that is, from my perspective, extremely nice. We have now a concept of placeholders. You already know one placeholder, which is auto. This is a so-called unconstrained placeholder, but now we have constrained placeholder. So the syntax comes together. I will come to this point later. Then, of course, you can define your own concept if the concepts are not available. And they can be used for all kinds of templates. Okay, that was only the overview. The long history. I think I first heard about concepts around 24, 25, so quite a long time. And I was totally impressed. And the first impression I got was, it's a little bit the kind such as type classes in Haskell. These are type classes in Haskell. They describe interfaces for similar types. They also build a kind of a type classes hierarchy, you see? In case your type should be audible, it should support a type class equality. And you can guess what that means. And that is, from my perspective, extremely nice in Haskell. Because now you can define a function which says, I only want to have a type which supports the show type class because I want to show it to the user, or something like that. And that was my first expression. But concepts are a little bit different, but anyway, I will mention it here. And this is the sad story, or it was the sad story to concepts. In 29, they were removed in from C++, in particular from C++11. It happened, as far as I know, in Frankfurt. And this was a statement from Bjarne into a monastery of complexity. They were too complex. The only compiler which actually supported concepts was the GCC, and as far as I know, the main reason why they were removed was, first, only one compiler supported them, GCC, and second, the compile time increased a lot, and that was not tolerable. This changed with the new concepts. Then there was the second attempt to bring them to the new C++ standard. Now they were called Concepts Lite, but the Lite is now gone, and we have now concepts in C++20. Okay, let's continue. Now a little bit, I want to show you what you can do with concepts. Okay, there are 3 ways to use it. I only display you 2, but that's enough. Have a look. Here, that is the nice way from my perspective. This is syntactic sugar for this way. Here I say, my container should support the concept of sortable, whatever that means. And this is the more verbose way. It requires that container is sortable. That is the way I describe in my function template signature what types should support. And here's the error message I got with C++ to GCC. If I use a list, I get this error message. Why? Because a list, particularly a stud list, only supports a bidirectional iterator, but not a random access iterator. But the implementation of sort requires a random access iterator. This is a nice error message. If you don't believe me, try this with type name and you will see what ugly error message you will get in case you don't use a concept. Okay. Looks quite comfortable, and this describes, one case it's a kind of a documentation, in another case it's a kind of a contract. And here I have to say something. A concept must be a constant expression in a predicate. Constant expression means it is evaluated at compile time, so at runtime you don't care. It's a compile time story. And predicate means it should be a function, or there must be a function which returns a boolean, meaning true or false. And only if it returns true, it will work. If not, the compiler will complain. Okay. Let's continue. You can also do it for classes. Here, that is my vector, which only accepts an object. And a reference is not an object. Therefore, I got this error message with a GCC. I only show you a few simple examples. The more interesting one will come later. Okay, you can use it for functions or for function templates. You can use it for class templates. You can use it for methods. Have a look. This is my vector from before, but now I require that the pushback method requires, which is part of the class template, that T is copyable. And in this case, it's special for a method, you have to place the concept before. Okay, so we can use it also for methods of class templates. Okay, let's continue. You can, of course, use more concepts, not only one concept. This is the find algorithm, and it requires that the container S is a sequence. In C++ terminology, that means something from a stud array to a stud forward list, something in between. So stud array, stud vector, stud deck, stud list, stud forward list will work in this case. And it requires that the value type, the elements of S, are equality comparable. If not, find will not work. So I use two concepts here. I think it's quite easy to read, and you can just read the declaration of the header and you know what should go inside and what not. Okay, we can also overload. There are a lot of variation of advanced. This is my variation. This is stud advanced. Who knows stud advanced? Then I have to ask the other way around, who don't know stud advanced? Sorry, that's always my joke I make if I get no answer. So forget about it. So stud advanced is quite easy. You have an iterator and you can advance the iterator by n positions. That's the idea. And the idea is I implemented for a simple input iterator, for a more advanced bidirectional iterator, and for a highly advanced random access iterator. These are iterators which are this one is more powerful than this one. And now I can use stud list int. I invoke, you see it, stud advanced int. I want to put it 2 positions ahead. And I say e, comma 2. And in this case, stud list is a, you know what a stud list is? It's a double-ended list of single nodes. So it only supports a bidirectional iterator. In this case, this algorithm is used. And why is this a good idea to overload it? Because if I would use stud vector supports, or stud array or stud deck supports a random access iterator, and with a random access iterator to put it 2 positions further, I can just do internally pointer arithmetic, which is a lot faster than saying 2 times next. So it's just an optimization story. So each container gets the algorithm it deserves. Okay. We can also do a kind of specialization. I have here, this is called a primary template, so no constraint on this one. And here I constrain it, it's a partial specialization for object. If you don't know what an object is, this is in well-defined time, you have to look up in CP reference, but I don't care for this presentation. If I use it with int, this is an object, but if ref, no, this is not an object, this is a reference, this one will go to the general case and this one will go to the partial specialization. Okay. Now to the fun stuff. But first I have to make a detour. You know what I like about C++ 14, but also what I dislike about C++ 14. I'm a trainer, I have to explain the stuff. And what I like about C++ 14, we have generic lambdas. Maybe you know, I assume you know it. You just put auto in here and you have a generic lambda. And what is a generic lambda under the hood? A function template. You know what I dislike about this syntax? We invented with C++ 14 a new way to define function templates. The first time I recognized it, I was really astonished. That's a new way to define function templates without sharp brackets. What I dislike is I cannot use auto in a function definition or declaration. It's not possible in C++ 14. And that is the way why I don't like it, because that is an exception to the rule. I don't like exception. I want to explain concepts. Not concepts in a concept sense, but concepts in a general idea than meaning. And this is what I didn't like. And this asymmetry is gone with C++ 20. The rule is quite easy. Every time you use auto, you can now use a concept. We talk about unconstrained placeholder and constrained placeholder. You will see how nice this will look like in a few seconds. Okay. Here, that is totally only an example. To be honest, this is not the exact syntax we will get in C++ 20 to define a concept. The reason why I used it here is GCC only supports this syntax, which was part of the Concept TS, Concept Technical Specification. In the call and the new C++ standard, it looks a little bit different, only a little bit, so don't care about it. But I cannot use it, so I cannot show you an example, I cannot prove it's right or it's wrong. So I use the old syntax. I will show you in a few seconds the new syntax. It's not so different. Have a look, this is a concept, and this concept says integral. And I use under the hood the function of the type traits library is integral to decide at compile time if t is integral or not. That means this would work if I use bool, int, short, long int, and so on for t. It would not work if I would use maybe an float, because it's a different type category. Okay, then I use it in my GCD. You see it here? And here I apply it. Only to see it work. And now you see what happens if I use it with a double. This is the error message I got with GCC, I don't know, 5.6, I don't know. But this is the error message I get. Oh, German localized. And I assume you know what that means, error. And you see constraints not satisfied. And why not? Because this is not, double is not an integral. Double is a floating point. Okay, this is the syntax, but we can do better. Now I talk a little bit about constraints and unconstrained concepts. Once more the concept from before, and here I use the concept only in the return value. I will come to the arguments later. Here I say integral auto, you see? With C++, 11, you could say auto for deducing the return type. Now you can say, deduce me the return type, but the return type must be an integral. The first syntax for concepts was different. In this one, you have only to use integral, but now you have to use integral auto. This is the C++20 syntax. Okay, you see? Now I can use it. In each place you use auto, you can let's say integral auto. In a range-based for loop. In initialization of my bool. Here also. And this one you know from C++11. This is C++11 and that is C++20. So, in each place in which you use auto, you can now just use a concept, which is just a constraint concept. Okay, let's continue. Only the proof, it worked. So forget about it. It worked. Okay, now I come to the syntactic sugar, which is for me the part I like most. And I will start with this one. A few syntactic variations. All of them are fine. I define GCD in 3-4 different versions. Here I use this requires. Here I put the integral here. And that is the point you should look at. This is the so-called abbreviated function templates syntax. This is part of C++20. I use as arguments, not a concrete type, not auto, I use just a concept. And that is a function template. Point. Which requires that the arguments are integral, as you can read it. And that is for me an extremely nice way to define a function template without sharp brackets. And you see what I meant by the syntax comes together. I can also use in C++20 auto in a function declaration, and it will become also a function template. But in this case, this is an unconstrained function template. It's semantically similar to a function template with type name. Once more, I totally like this syntax, this one in particular. And now maybe your customers are not afraid to define a template, to see it from the other way around. Because it looks quite natural, and you see from the declaration what's the contract, what could be used as a type. It's a kind, in Python, we always say explicit is better than implicit, and that is as explicit as possible. That is, for me, fine. Okay, just to prove it, it works. Okay. But you know what the GCD from 10 and 100 is, so it's not a point here. Okay, let's continue. We can also overload on this new syntax. Have a look here. Overload auto, that is an unconstrained placeholder, that is a constrained placeholder, and that is just a function. They overload. And if you invoke them now, the compiler will pick the right one or the best fitting one. Meaning it will use a pattern matching to the best fitting strategy. In case of float, this one will not work, this one will work, it will go with the general one. In case of int, this one will work, so it uses this version. In case of long int, this should be an L, it goes to the long case. Okay. Now this slide is written in red letter. The reason is quite simple. I assume we will not get it with C++20. That was part of the Concept TS proposal, but one little part was not accepted, and as far as I know, template introduction. But as I mentioned it already, I'm not totally sure. So this is the template introduction. The key idea is there's a new way to define a template. Instead of template integral T, you can just say integral T. This was the idea. And what I didn't like about this syntax is, this syntax only works for constrained placeholders, but not for unconstrained placeholders, such as auto. You know what I don't like? Exceptions. And this is a new exception, because I have to remember it, I have to explain it. But actually, this is not a strong requirement. You can overcome it. Let's have a look here. Here I use integral t. Here I use this new syntax, which I'm not sure if you will get it. And you see that's the GCD used with this template introduction syntax. That is the case for function template, and that is the case, in this case, for a class template. But this will not work with auto because it will only work for a constrained placeholder, not for an unconstrained placeholder. But there's an easy trick to overcome this issue. Just define a concept which always evaluates to true, which is crazy. So now you can do it. This was with the GCC and it worked. I did it for the function template. That is conceptually a function template without constraints. And I did it for a class template. And sorry for this line. We hate and love C++ in the same sense for this line. This line just returned me a string representation of the type T here. Forget about the other stuff. Okay, and now when I use it, you see it, in case if I use it with an int, I will get back an E. If I use a std string, I will get this string representation. And if I would use in double, I would get back this string representation. D stands for double. This is the ugly LTTI we have with with GCC and Clang. They always give back extremely ugly types. With Windows, these types would be really nice to read, but with Windows, I could not use concept, so I stick to GCC. With Windows, it would actually write std string here and not the type def which is under the hood. Okay. Now I come to defining concepts. Okay. First of all, don't define a concept because maybe it's a variable. Eric Niebler's ranges library has a lot of concepts. The standard defines a lot of concepts. Have a look. This stuff is all available. You have core language concepts such as same, derived from, convertible to, common, integral, you saw it. I defined it to show it to you, but you have not to do it. You have integral, signed integral, unsigned, assignable, swappable. I assume you know what that means. Then you have comparison concepts such as Boolean, equality comparable, and strict totally ordered. We have concepts such as object concepts, destructible, constructible, default, move constructible, copy constructible, movable, copyable, semi-regular, regular. I will come to these concepts because I will implement both of them for you. This is one of my examples I will show to you. Regular and semi-regular. And then we have concepts for callable such as callable, regular, callable, predicate. It's a callable which returns a Boolean, and so on and so on. These are not all concepts, but I only mentioned a few of them. So there's no need to define them. In particular, both concepts I define now are already defined. So forget it. I'm not sure if they define it the same way, but I did it in this way. Okay, this is the concept. You can do it as a kind of a variable. This is quite easy to use. Integral, you saw before, I used this type traits, which is available since C++ 11, to check at compile time, is T an integral type or not? Okay. Okay, if is integral equals to true, it will work, if not, not. And that is the function syntax which looks a little bit like the function, and here I compare this concepts TS syntax and the syntax which will go into C++ standard with high probability. Here you see it, and you see that is a little bit similar. This bool is gone, this curly braces are gone. Instead of curly braces open, you have an equal sign up, but besides that they are quite similar. That is the syntax which will go into C++ standard, but as far as I know, no compiler supports it. Only the old version, so I worked with the old version. Okay, what does this concept mean? I defined the concept equal. It means both must have the same type. The operation equal and unequal must be available, and it should return a bool. This is my concept. That is for me the concept equal. It only works for the same type, and equal and unequal sign must be available, and both are predicates. Operation must be available, and both are predicates. Okay, let me show you a simple example, and then we'll show what error message we will get. Have a look here. Here I define a function which is extremely small, which only returns if both arguments are equal. So it returns true or false. But I say here, both types must support the concept equal, as I defined it before. Now I use it. Here, this is the stuff and type which don't support equal because I deleted it. And this type don't support unequal because I also deleted it. Only to show you the error message in case if I use them. Here I use it with an integer, and you know of course that an integer supports comparison, so I can use the equal sign. And then I use in the second case all the stuff which is commented out here. This one and this one. This is the good case and this is the bad case. Now you see what happens. This is the good case, of course that's easy. And that is the bad case. This is the error message I got with GCC, I don't know, what was it? No. I have just to use the flag -f concepts, and you see constraint not satisfied, constraint not satisfied, and here it says why. You have now not this expression, and you don't support this operator, and the same here. I just used it and you see what happened. This is a compile time error, of course. And it's, for me, it's a little bit tough to read, but at least it's good readable. It's not a template instantiation error. It's a you broke the contract. Okay, now a little bit Haskell. Why? Because as I looked at this, when I looked at this feature, I want to know, can I be as elegant as to program as in Haskell? And here in Haskell, this is the equality type class. And you see it looks quite similar, not so different. And I will come to this point with Haskell in a few seconds. Here it says a type A supports equality if it supports the equal and unequal operator. Both must have the same type and they should return bool. And that is the same stuff I write here. That is the concept equal, you saw it before. Left the Haskell, right the C++ syntax. And now to the interesting part. I want to show if I can do something similar, such as here in C++, defining a concept ordering which requires that the type is equal. Not by defining each function, but by using an existing concept. It's a kind of a type hierarchy, which we have here in Haskell, you see. You see, that's a kind of a type hierarchy. And my idea was, can I show that I can do the same in C++? Of course I can. If not, I would not say it to you. That is equal from the Haskell perspective. Equal ordering of A requires that that A is, supports the type class equal, and that is the stuff which ordering additionally requires. This comparison operators, then the function compare and the function max. I will skip compare and max in my C++ case now because it's only a little bit more to write, it's not an issue. I only show you that I can do something similar, but I only implement the comparison operators. And that is the solution in C++. You know it? That's the concept equal. Then I defined the concept ordering, and I say it requires that t supports equal. And then I add the new requirements to it. So I use an existing concept and refine it to ordering. With a little bit of work, I can implement this Haskell type hierarchy in C++. It's just stuff I have to write. And for me, that is quite elegant. I can build a type hierarchy. Okay, let me try it out. Here, the same algorithm from before, are equal, and here gets smaller. Here I require that A and B supports the ordering concept. Not this weaker one, the equal, but the ordering. This is the good case, that is the bad case. You will see it in 5 seconds. Have a look. I say 1 and 5 are equal, will work. I have 2 unordered sets, and I will check if they are equal. Maybe you know it. Unordered set supports only ordering, supports only equality or inequality, but not ordering, because it's called unordered. So it's quite obvious. So if I use this unordered set in this function get smaller, I should get an error, because there's no ordering guaranteed or no ordering defined on the keys. Okay? Now you see it. That's the good case and that's the bad case. You see? Constraints not satisfied, and that is the concrete reason. Would be ill-formed. Now that was my proof. I can be as elegant as in Haskell. Now to my second example, which is a little bit more complicated, but this is my last one. We have in C++ the concept of regular and semi-regular types. I will not say what that means, but under the hood it means if you have a regular type, in short you say it behaves such as an int, or you can say it in a different way, it works smoothly with the standard template library. That is a regular type. What is a regular type? It should support this kind of concepts. They are quite easy to remember. You know the big 6? Default constructor, destructor, copy move assignment, copy move constructor. Here they are. And then you have to add swappable and equality comparable. Then you are regular. So the big 6 and additional swappable and equality comparable. If you subtract equality comparable, you have only semi-regular. These are the terms which are actually from Alexander Stepanov's book. Okay, now I tried out if I can write a concept regular and semi-regular to check it. Okay, of course I have to use something which can be evaluated at compile time, so I use this type traits from the standard template library. I have already all functions I need, only one is missing. Equality comparable. There's no way in the type traits to ask for equality comparable. That means a type which answers all questions here with true is semi-regular, but not regular. You see it here. But you see, for example, an int ref is not default constructible. I will come to this later. Okay, how can I achieve that? That is an ugly slide, but sometimes Sphene is ugly. What is the idea? With C++ 20 we will get with, I don't know if we will get it. I have to use it experimental. This is the so-called detection idiom. What is the idea? I define my own type traits which I can use at compile time to detect if T is equal comparable. That's the key idea. I say deckel of T, and that returns here true if of type T is equally comparable at compile time, of course. This is a type trait which only answered me the question. I have an int. Is it equal comparable? Yes. But for another type, maybe no. And that is the type trait I need for define the type, the concept regular. And if you are curious, look at the detection idiom in C++. Maybe you can read your book. Did you play with this stuff, Davide? Sorry?
But anyway, yeah, there are some.
Yeah, Sphere is ugly. This is so ugly, but sorry, Sphere is ugly. Always I show it in my classes. That is the last part I do in my class. Afterwards they go. Okay, now I can use it. You see, I can define is semi-regular. This is my type trait, which will detect at compile time if my type is semi-regular. It supports default constructible and copy constructible, copy assignable, movable. This was the easy part. And that is regular. Regular means it must be semi-regular and it should support my new type traits. And if I would now use, here is the use case. If I would now use this in a concept, I can now define the concept regular in semi-regular. Now I have the concept. So I can use the concepts regular and semi-regular in my function declaration, and it becomes a function template which satisfies this concept. As far as I know, regular and semi-regular are already defined in the standards. I don't know how, but maybe in this way, I don't know it. Okay, now I'm nearly done. Now I come to the key question. Is this an evolution or is this a revolution? I wrote 1 or 2 years ago in a German magazine article about concepts. They called it revolution, and now I say maybe they are right. Why is this a revolution? But first of all, what are the arguments for evolution or revolution? What is assigned for evolution? Of course, we have auto, we have unconstrained placeholders, so we have a concept for, we have an idea of placeholders, so it's not so new. Of course, we have with C++ 14 created a new way to define function templates. This is a kind of the evolution part. But we have the first time the possibility that a compiler can verify template requirements. That is evolutionary. That's not revolution. That's evolution. Revolution, not evolution. Second, declarations and definitions of templates radically improve. You saw it. You just use a concept in a function declaration and it becomes a function template. And that is my main point because it's written in bold letters. Now we can define semantic categories for templates. What does that mean? I could define categories such as regular, semi-regular, such as audible, such as equal. That's a new way to express my logic in source code. And that is for me the main reason why I say this is for me a revolution, not an evolution. Maybe we will define groups in the mathematical sense or half groups, or I study mathematics. This is a new way to think about software from my perspective. Okay, I'm done. I have no question. Maybe you. Do we need a mic or do we have a mic or should you can cry?
Okay, I try to speak loud.
No, just more.
Okay.
Okay, we have one.
Thank you. I can expect that concepts combines together with auto ampersand like expected, right? For the universal references.
Maybe you are. I'm not sure. I know what you mean, but I'm not sure what that means. In the
expected in the sense that I would expect that the concept is applied to the type, decal type auto, yeah. Not the ampersand, whatever. The question is, what about the decal type auto for the return type and the concept?
I don't know it exactly, but the point is instead of auto, you can also use Deckel type auto. You see integral auto, but you can also say integral Deckel type auto, which is the new syntax we got with C++14 for defining the return type of a function, which is exact, and you can also apply it to integral. I never thought about consequences, but we can at least do it.
Thank you.
You were mentioning that one of the reasons why the concepts were initially discarded was worse compile times. Do you know if this issue has been solved or?
To be honest, I don't know it exactly, but I heard a few comments which said maybe it's about 10% slower to compile the source code, but only 10%, not 100%, as with GCC concept version 1. I always say in C++, C++ is optimized for runtime, not for compile time. But anyway, we also look at compile time.
Yeah, I think we all know that. So
yeah, you know, you have sometimes systems which have a build time from 1 day. You cannot say, maybe you are better, but it will take 2 days to build your software.
Okay, thank you very much.
If you have a directly answer to the question.
You know Eric Niebler, the author of the range library.
The Eric, you talk about Eric.
Yeah.
Eric Niebler, the author of the range library, shared some evidence that doing constraint checks with concepts improves compile time.
Improves?
Over manually handcrafted checks.
I have
okay, good. So if you use like different techniques for constraining template parameters with these concepts, he said he got an improvement of about 10-15% in compile time.
That is a killer argument.
This is anecdotal evidence, so not a scientific measurement, but...
To be honest, my numbers are for concept slide. They thought this is a new version. And the second point is, he mentioned Eric Niebler's ranges library. The ranges library is the first big customer of concepts.
Yes.
Without concepts, there would not be a ranges library. Yeah, but
you showed an example before where you used the concept to in the variable declaration, so integral auto variable name equals something. Does the concept there change the behavior of auto or just validate the result of auto?
The point is, if you say into auto equal A, and A is not something integral, it will break during compile time.
But it will not kind of change the behavior in a way that now it will convert to something
else?
else?
No, forget about it. This would be terrible. I never thought about it, but this would be terrible. Time is over, sorry. Okay.